So in our last lecture, we looked at double integrals over rectangles. Obviously, we don't expect the domain of definition of any function, of every function, to be a rectangle. So it's important to see what will happen if we have a function which is defined on a set which is not a rectangle. Well, our starting point is going to be slightly more specific domains of definition. So let's start with the following situation. So imagine that you have a domain of definition that looks like this. So I'm going to draw it on the xy plane. So this is the x-axis, this is the y-axis. So supposedly, and to understand what is going on here, we're talking about two variables. So I'm going to draw for you what I have right here as the domain of definition, and then the graph is something up here, right? This is the general idea that we have explained. So in this case, I'm going to draw it a little differently. I want my domain to look like this. So I have a certain graph on the top. So let's call this G2. It's funny that I start with G2. I would like to start with this one. So let's say I have this one is G1 of X. And we want to go from A to B. So imagine that this is precisely the domain that you have here, meaning this one. So that's what I was trying to draw right here. And we can actually describe this domain quite specifically. And this is the domain D, let's call it D. And it's all xy's such that y is between G1 of X and G2 of X, and X is falling between A and B. And here you can see why. I mean, if you take any X which is between A and B, so let's say this is your specific X, then for that specific X, the Y's that give you this segment that lies in your domain are the ones that lie between G1 of X and G2 of X, which is up here. And of course, you can see that as you move to different X's, G1 of X and G2 of X will in general change. So here comes the idea, which actually we could explain why we get this. The idea is that you could consider this as being part of a rectangle. And once it's part of a rectangle, then you can apply the iteration that the iterated integral, the formula with the iterated integral that we presented last time. And the only part that will matter is the part that is between G1 of X and G2 of X. Of course, we have to specify what will be the new function that you will be defining on that interval. And pretty much what is going to be the idea is that the new function is going to be 0 outside the domain, meaning if you were to try to visualize the graph of such a function, then you would have the portion up here, and then the rest of the graph would be down here because supposedly your function is 0 outside the domain. Such a function, unfortunately, would not be continuous. And even though we didn't say that explicitly last time, the theory is presented in the most straightforward way for continuous functions. As long as the boundary is good enough, then everything that we said last time can be actually carried out for this type of functions. And this is where you would get the formula that we're going to write right away. And the formula is as follows. The double integral over d of f of x, y, dA. So the idea is that I want to write this as an iterated integral. And when you have such a description, you always begin with this variable right here. So you go with respect to y of f of x, y. What is going to be now different, radically different from what you had in the case of the rectangle, is now the endpoints are going to vary. Okay. And then you're going to eventually integrate from A to B. And there are many remarks to be made here. So first of all, this is exactly, remember that little presentation, that little trick that we gave in the end of our last presentation, which said that if your integrand is the product of two functions over a rectangle, then you can split the integral. This is precisely where this trick breaks down. You cannot do this if you have non-constant endpoints. Okay, so that trick is out of the window. You just need to do usual iterated integration. Now, please understand that there's no particular reason why this could be done first with y and then with x. Depending on what the domain looks like, it can be done the other way around. So in particular, let me also give the following case. So imagine now that you have a domain that has a left curve that defines it and a right curve. And let's say that this is x is equal to g1 of y, and this is x is equal to g2 of y. And then you're just going to go between C and D. So if we were to describe this domain the way we did before, so let's say that we call this D, then D is going to be all x's and y's such that x is between g1 of y and g2 of y, and y is between C and D. So in a completely analogous way, if you want to take the double integral over D of a function f of x, y, and you're going to see that in this kind of consideration, the last thing that we care about is the integrand. This game is pretty much played with a domain, and if you would like to isolate, excuse me, the challenge that you encounter in this kind of integrals, then the main challenge is to actually express your double integral as an iterated integral. So here, you will go with integration, first of all, with respect to x, as you can see here. Sometimes I will refer to this as horizontal integration. So you're integrating the function f of x, y, and you will go from g1 of y to g2 of y. So if you think about it, this integral will depend on y, and then eventually you will go from C to D with respect to y. And we have our iterated integral. Occasionally, you may find domains where you can do it both ways. And the other thing that I should mention here is that you have to be careful about the fact that whenever you have these iterated integrals, and we're going to see also triple iterated integrals pretty soon, the outer limits should always be constant numbers, at least in this course. Okay, so if you have outer limits on the outer integral that involve variables, then you're doing something wrong, because potentially if you do that, you're going to find a function, not a number. And I'm not saying that this is impossible, that we cannot encounter cases in which we just need to do just that, but it's not going to be the usual way, or it's not going to be what you're going to see in this course. So here's what I'm suggesting now. Before we actually do numerical examples, let's do a couple of examples where we try to give such iterated integrals, since the whole idea here is to produce these iterated integrals. So let's give some examples where we don't even specify what the function f of xy is. Here, again, pretty much our considerations are all about the domain. Before I give any examples, I should mention something else, that now that the domains become more interesting, all of a sudden there is another interpretation of the double integral in a more specific, in a more special case. So imagine that you have a domain A. Then if you imagine the function, the constant function 1, then the volume of this region, so imagine that this is the function z is equal to 1, or f of xy will be equal to 1, then what you get is what we might call a prism. And exactly because the height is equal to 1 right here, the volume of this prism, numerically speaking, it's going to be exactly equal to the area of the domain of definition. So in other words, if you integrate the function 1, and sometimes you can even skip the number 1, just write dA, you're going to get the area of D. So this is another formula that, as opposed to the initial interpretation of the integral, which was 3D volume, it tells you that if you specifically integrate the function 1, you can interpret what you find as the area of the domain. That would have been, of course, the case in one variable, where if you integrate the function 1, then you find the length of the interval. But back then, the length of the interval was something so straightforward to find, so easy to find, that nobody would bother pointing out this specific case. Whereas here, you may actually find cases where the finding the area might lead you to a double integral, where you can apply more methods, as we're going to see. Again, here somebody might say, isn't this covered already since it's area by one variable? The answer is, in many cases it is, not necessarily always. There are some interesting cases that we're going to explore later. But it introduces this kind of general concept, according to which if you take the integral of the function 1, then you find the measure of the set over which you're integrating. So let's begin with a couple of examples that involve just the consideration of the domain. And you know what? Let's start with the unit disk. So the unit disk has as its boundary x squared plus y squared is equal to 1. And let's say that this is the domain D. And let's say that somebody asks us to write or to compute the integral of some function that, again, I'm not even going to bother disclosing here, over the domain D, because the whole purpose of this consideration is to write it as an iterated integral. So what are we going to do? First of all, we're going to choose the direction over which we're going to integrate first. And let's say, for the sake of the argument, that we decide to integrate first with respect to y, and then with respect to x. So in other words, the way that I would like to put it is, we're going to have vertical integration first. In such a case, we need to figure out what the lower boundary curve is and what the upper boundary curve is. So what is the lower boundary curve? Well, it all comes to solving for y here and taking one of the possibilities. So if you solve for y, this equation right here, then one of the possibilities that you get, let me actually show it. It's y squared is equal to 1 minus x squared. And now you're ready to take to guess what numbers have square equal to 1 minus x squared. And of course, it's the square root, but you can also go with the opposite of the square root. The square root is always positive. And the graph of this specific function that I'm drawing here is, of course, with the negative sign. And if you were to take the upper part of the boundary, then you would find simply the square root without any sign. So now you have your boundary curves, and exactly because you do a vertical integration first, it's precisely these two that you're going to put as your bottom boundary and the upper one. So square root of 1 minus x squared to square root of 1 minus x squared. And then you can ask, okay, so what is the range of all these vertical integrations? And basically you go from -1 here to 1 here. So it's going to be from -1 to 1. And of course, I'm going to put my integrand in between, about which I seriously couldn't care less. And this could have been done also by doing first horizontal integration and then vertical integration. So we could have something along these lines. So we could have let me change color so that it becomes a little more distinct. So we can have a left boundary curve and a right boundary curve. And how do we find those? Solve for x now, and the right boundary curve is going to be x is equal to square root of 1 minus y squared, and the left boundary curve is going to be x is equal to minus square root of 1 minus y squared. So if we want to write our integral as an iterated integral, then we have the integral over the double integral over t of f of x, y, dA. Remember, that's always our starting point. And then we're trying to write it as an iterated integral. So as we said, we're going to do horizontal integration first. And our leftmost boundary is going to be minus square root of 1 minus y squared to square root of 1 minus y squared. And the range of all this, the vertical range of all these horizontal integrations is going to be from -1 to 1. And our integrand, like I said, we're not trying to do a computation here, but this is how we would handle the domain if we chose. And in this particular case, it is possible to be done both ways, but if we chose the second way. So let's do now one more such example where we focus on the domain before we do any particular integration. And this time, let's take a triangle now. Okay, this is going to be a little more interesting. So take the point 0, 1 up here. Take the point 1, 0 here. And take the point -1, 0 here. Okay, and let's say that this is the domain D. And the question is, what would be simpler here, to do horizontal or vertical integration first? We're going to do both. Let me just say that these boundary curves, this is x plus y is equal to 1. Please note that I'm giving it to you in a symmetric way. And if we wanted to use it in any other if we want to use it in the integration, then we will have to solve for x or y. It's the same thing as we did before with the circle, where the circle was initially given as x squared plus y squared is equal to 1, and then we solved for either x or y depending on what we wanted to do first. So in any case, let's suppose here that we do horizontal integration first, and you will see why horizontal integration is a little more convenient. So you want to solve for x here, and in that sense, x is equal to y minus 1 if you isolate x, and here x is equal to 1 minus y. So if you had the integral over d of a function f of xy over the domain D, and you wanted to execute first your horizontal integration, then you would have to worry about the left boundary, and the left boundary would be y minus 1, then about the right boundary, which would be 1 minus y. And the vertical range of all these integrations is from 0 to 1. So you would have dy from 0 to 1. Of course, you have your integrand here. And that's how we represent our integral as an iterated integral. And now the question is, what would happen if we wanted to go the other way? Meaning, let's say that I wanted to go first with respect to y, and then with respect to x. Well, here we have to, first of all, clarify that it's not true that in every given setup that's going to be a possibility without writing more than one integrals. In general, for most domains it is, but in many cases you have to actually use more than one integrals, and that's exactly the case here, because if you now ask, what is the upper boundary? The upper boundary is this now, right? It's this curve. And this curve, unfortunately, doesn't have a single equation that gives it, meaning from -1 to 0, it's by y is equal to x plus 1. And from 0 to 1, you have a different line, which is 1 minus x. So what this means is that the integral here will go from 0, y0, because the bottom boundary is simply the x-axis, and the x-axis is y is equal to 0. So from 0 to x plus 1, but this x plus 1 is valid where? Not for all the x's, simply from -1 to 0. So this expression that I just wrote down is not going to give you the integral over the full domain. It's going to give you the integral over simply this part, which means that you will need a second part where now you're going to go from 0 to the boundary being 1 minus x of the function f of x y dy again. But now the horizontal range over which this is valid is from 0 all the way to 1. And so we see this very, very useful example, which I would advise you to here to stop, for which I would advise you to stop to pause the recording and try to do it yourselves. Try to see all the geometry of this domain, where we have to break the integral into two integrals in order to write them as iterated integrals. And again, the reason that we have to do that is because the upper boundary is not given by just a single expression. I mean, one could try to find a single expression, but it would be much, much more complicated and not helpful for the problem. And that's why the natural thing is to break it into two integrals. So let's do a numerical example. Let's try now to see how this works. And let's suppose that we take this point 0, 2, and this point 1, 0, and here's our domain D. And we would like to compute the integral, double integral of xy dA over D. And I'm giving you this as a little tease because you can see that the integrand is xy, but you should not be tempted to split this integral exactly because it's not over a rectangle. So first of all, let's agree that we're going to perform vertical integration first. And so we will need the lower boundary. Let me put some colors here so that you can see it. So you have the lower boundary, which is just the x-axis being y equals 0. And how about the upper boundary? The upper boundary is this, right? So what is this line? This line is actually x plus y over 2 is equal to 1. And here you want to solve for y, because you're integrating vertically first. I mean, whatever variable you have here, that's the one you want to solve with respect to, which will give you y is equal to 2 times 1 minus x. And let me make a quick note about how I found this formula right here so easily. In general, whenever you have a straight line that intersects the x and the y axis at two non-zero numbers, then you have that the equation is x over a plus y over b is equal to 1. And why is that? This is a linear equation, so it represents a line. And it's very easy to see that this point, which is a comma 0, and this point, which is 0 comma b, actually fit into that equation. This is sometimes called the equation of the intercepts. And as we're going to see, there is an analog for planes. So this little trick allows you to find very easily such equations. And let me go back to the computation of my integral. Again, the most important part of the whole process is to write it as an iterated integral. So dy now will go from 0. We have solved in terms of y the upper boundary. So this will be 2 times 1 minus x. And we also have the horizontal integration. So when you do vertical integrations first, then you want to see what the horizontal range of all these vertical integrations is. And this is going to go from 0 to 1. And in this particular case, we want to do all the math involved and show how the iterated integral can be found. So we're integrating with respect to y first. So it's going to be 0 to 1. So we're thinking of x as constant. And then the antiderivative is going to be xy squared over 2. And we're supposed to go from 0 to 2 times 1 minus x. So this is the new thing that we will be facing here, that now we're plugging in things that are not just constant numbers as it happened in the case of the rectangles, but they can be non-constants. And this is going to be the integral from 0 to 1 of x. So when you plug in 2 times 1 minus x as squared, you will get times 4, 1 minus x squared over 2. I'm sorry, this doesn't change. And so you can have it's a pretty straightforward integral, but let's finish the integration. You can hand this integral to any friend of yours that has taken Calc 1 or Calc 2, depending on when you do such simple integrals. So 0 to 1. And you have 2x times 1 minus 2x plus x squared. That's the square of this. And this will give you the integral from 0 to 1 of 2x minus 4x squared plus 2x cubed. Always when you do these lectures, please try to do the examples, the numerical examples yourselves, and there might be numerical errors here. I will try not to make such numerical errors, but it's not necessarily going to be a guarantee that it will not happen. So what is the antiderivative here? So we will have x squared minus 4/3 x cubed plus 2 times x cubed over x to the 4th over 4. So this will be 1/2 x to the 4th. And we want to go from 0 to 1. So this will give us 1 minus 4/3 plus 1/2. And this is going to be, so 6 is the common denominator, minus 8 plus 3 over 6, which is 1/6. And it's important to note here something very, very useful. I mean, look at the integrand. It's xy, right? Over this domain, the quantity xy is actually non-negative. So you're integrating a non-negative function. So the graph, if you were to try to represent the graph here, it would be somewhere over the xy plane. So the region that you get must have positive volume in the sense of the signed volume that we get in double integral. So it's a little bit of a fail-safe in the end to make sure that we got a positive number. If we got a negative number for such a function that happens to be non-negative over this specific domain, then we know that we would have made some mistake. Okay, now let's go to a very interesting little situation that can be created here. So imagine that you have a situation where an integral is actually, an iterated integral is given to you. So you don't even have to bother writing your double integral as an iterated integral. So if you go back to the previous example, if somebody was to give you from the very beginning this expression, then you didn't even have to know what domain you had or anything like that. And you could just proceed and take the steps the way that we just showed. And here's something very interesting. So imagine that somebody tells you the following. So compute the double integral of e to the x squared dx from y to 1, 0 to 1 dy. So imagine that somebody gives you this iterated integral. So you might think at first that, oh, okay, so this is a gift. We can just compute the inner integral first, then the outer integral without any specific difficulty. But the problem is that the first integration, look at it. I mean, take a quick look at it. Is impossible, at least in a quite narrow sense, in the sense that you cannot find explicitly the antiderivative, at least in terms of simple functions, of e to the x squared. Of course, the antiderivative of e to the x squared exists, or an antiderivative, because there are infinitely many of them. But you cannot have a simple formula for it, which makes the task of computing this integral impossible. And here comes the interesting situation. So we have this iterated integral, and we entertain the possibility that since this can be guessed to have come up from a double integral, that when somebody who was given the double integral came up with the integration in this order, first with respect to x, then with respect to y, and we end up with this dead end. If instead of going first with respect to x, then with respect to y, we had gone the other way around, what if the integration was possible? And this is a big if. I mean, you don't know that that would necessarily be the case, but at least you want to give it a try. So the problem is, how do you change the order of integration for an integral where you don't even know what the domain was to begin with? And that's exactly the main point. So the main point is that you have to find the domain. So how do you find the domain? The idea is pretty simple. Let's try to sketch it. So what does this integral have to tell us? It tells us that there is horizontal integration first, right? It's with respect to x. So when there is horizontal integration, you go with a left boundary and the right boundary. The left boundary is what? That says that it's x is equal to y. It's always going to be the variable you're integrating with respect to equals whatever expression you have. And this is going to be x equals 1. So ask yourselves, what are the lines? And there are lines here. In general, there could be more general curves. What are the lines x equals y and x equals 1? And x equals y is the bisector of the first quadrant. And x equals 1 is this vertical line, right? So this is x equals 1, and this is x equals y. And you know that horizontal integration takes place somewhere between these two lines. Yes, but can you be a little more specific? Which part of this region would be? And the answer to this is provided by the vertical limits, 0 and 1. This tells you that you go from 0 all the way to 1, which is up here. So what this means is that your domain of integration is precisely this. And now that's the key to the problem. And I could not emphasize it more, that when you have a situation like this, you have to find the domain. Because once you have the domain, then you can actually reverse the order of integration. So now we say, okay, what if we went vertically first? If we went vertically first, then we would have to face a lower boundary and an upper boundary. And the lower boundary is the x-axis, which is y equals 0. The upper boundary is x equals y, as we said before, but now if you want to use it here, you have to write it as y equals x. So pretty much it's going to be from 0 to x. And then what is the horizontal range of all these vertical integrations? From 0 to 1. And now we have a little miracle, as we're going to see. The integrand is e to the x squared. But the thing that I would like to emphasize most is that that you should never try to go from this integral to that integral without going through the domain first. So this whole process always goes through the domain. So you have to sketch the domain, and you sketch the domain the way that we just showed. That is, you ask yourself, what is the first integration? And if the first integration is horizontal, like it is here, then you're going to have a left boundary and a right boundary. If it was vertical, then you would have had a lower boundary and an upper boundary that you would need to try to sketch. Now, here's what is interesting in this integral. Again, you can't split it. Why can't you split it? Here's the reason why you can't split it. You don't have constant endpoints. The only time you have constant endpoints is if you're integrating over a rectangle. And certainly this is not a rectangle. The domain is not a rectangle. So we have to take the first antiderivative. And the first antiderivative, think about it, you're integrating with respect to y, and this is constant. It's like having the number 7, right? So what is the antiderivative of 7? 7y. Well, it's going to be the same thing, y times e to the x squared from 0 to x dy dx. And you see what happens now? If you plug in x into y, of course, then you will get x e to the x squared minus 0 e to the x squared. The bottom line is it's x e to the x squared. And now you see this makes all difference in the world, because now you can apply substitution. So u is equal to x squared, du is equal to 2x dx, or x dx, which is exactly what you have, is 1/2 du. And this will allow you to go with an integral of e to the u times 1/2 du. You have to be careful with the endpoints, right? The endpoints are 0 and 1. I'm saying this because for this specific example, it might be a little misleading. Remember the formula of substitution. It's f of g of x, g prime of x dx, from a to b. It changes to the integral of f of u du from g of a to g of b. Of course, here the substitution will be u is equal to g of x, which means that du will be g prime of x dx. This is what you need to remember from substitution for the definite integral. And I'm saying this because when you take the square of 0, meaning when you plug in 0 into the substitution formula, and when you plug 1 into the substitution formula, you still find 0 and 1. And that might mislead you into thinking that nothing really changed, but everything has changed. It's just that 0 square is 0 and 1 square is 1, and we have got a little lucky here. But the bottom line is that this will be 1/2 e to the u. That's the antiderivative from 0 to 1, which will give you 1/2 e minus 1/2 e to the 0, which is simply 1/2. And sometimes people might write this e minus 1/2, but it doesn't matter. That's not the biggest concern of ours at this point. What is important to understand is the remark that we made in the very beginning. You have that you're given an iterated integral. Again, at least in the beginning, it's joy, right? We can't just compute the two integrals one after the other. Just be careful with what variable we're integrating with respect to. But then that joy becomes a little bit of a caution because we cannot integrate with respect to the first, we cannot complete easily or in a straightforward way the first integration. So then we ask ourselves if we could go with the second integration, with the other integration first. And in order to achieve that, in order to achieve the change of order of integration, we have to go through the domain. This is an example that it's important to do it several times to become comfortable and confident with how it's done. And that's all for today. Thanks for watching.